Hi, my name is Gupta Khan, and in this animation, we are using FET AC kit, and we will be looking at the relationship between the current and voltages across a resistor, a capacitor, and an inductor in an AC series circuit. So let's turn the switch on. Now, first of all, let's compare the current and the voltage across the resistor. The current is same everywhere in a series circuit. And if we compare the voltage across the resistor and the current, you can see that they are becoming maximum at the same time or minimum at the same time. Or we can say that voltage across the resistor and the current, they are in phase. Now, and you can see from here, they're both maximum or they're in phase. Let's compare the voltage across the capacitor and the voltage across the resistor. Voltage across the resistor is maximum. This one over here is 0. It has still reached its maximum value, and that will happen after quarter of a cycle. Or in other words, what we can say is that voltage across the capacitor is 90 degrees behind the voltage across the resistor or the current. Let's compare this one, voltage across the inductor. And if we look at the voltage across the inductor, this one is almost 0, and this one is maximum. So the voltage across the inductor has reached its maximum value, and now it's a little bit further ahead. So that means this time from here to there is quarter of a cycle, or voltage across the inductor is 90 degrees ahead of the voltage across the resistor or the voltage or the current in the circuit. If we compare these two together, then you can clearly see that this one has become 0 from a negative value, whereas this one has become 0 from a positive value, or in other words, that voltage across the capacitor and the voltage across the inductor, they have got an opposite phase, or they are 180 degrees out of the cycle. Let's turn it on again. So again, if you look over here, these ones, this one is, when this one is at a positive maximum value, this one is at a negative maximum value. Let's stop it. Right here. So voltage across the capacitor is negative maximum, voltage across the inductor is positive maximum value, so they've got exactly opposite phase. Whereas if you look over here, this one had already become negative value and it is now 0. So voltage across the resistor is 90 degrees ahead of the voltage across the capacitor. So that is the phase relationship between the current and the voltage across the resistor, capacitor, and inductor. How we will show it, if we want to show it in one graph, it would look something like this one. So again, this is about the same resistor, inductor, and capacitor circuit. So if you look over here, the black one, that's the current time graph. Blue one, that's the voltage across the resistor graph, and you can see that they are in phase. Green graph is the voltage across the capacitor, and this one is behind the voltage across the resistor by 90 degrees. So if this one becomes 0 after this much time, which is quarter of a cycle. And if we look at the voltage across the inductor, that is 90 degrees ahead of the voltage across the resistor because it has already become maximum. This one become maximum after quarter of a cycle. And if you compare the phase of the inductor and capacitor, it has got positive, this one is negative. Now they're both 0. Now capacitor is has got a positive value, or they have got a negative value, or they've got exactly opposite phase. So how we write these one is that voltage across the resistor and the current, they are in phase. VL leads VR by quarter a cycle, and VC lags VR by quarter of a cycle, and VL and VC, they've got opposite phase. Now, we can draw them by phases. So this is VL, VR, and VC. Conventionally, VR is always drawn here, and these phases show the value at different times in a circuit, and the phases move in an anti-clockwise direction. So again, from here, we can see that voltage across the inductor and the voltage across the resistor, they've got opposite phase. Since they've got opposite phase, so if we want to find what is the voltage across the inductor is more than the voltage across the capacitor, so we will have to minus this from that, draw another vector there. So that is VLN minus VC, and that's VR, and that's the supply voltage. So when voltage across the inductor is more than the voltage across the capacitor, the circuit is LCR circuit, but it behaves like if capacitor wasn't there, or it behaves like an inductive circuit. And again, we add them like in a vector manner. So V supply square is VL minus VC square, which is this one, plus VR square. Now, current is always in phase with the voltage across the resistor. So if, or in other words, what we are saying is that supply voltage is ahead of the current by these many degrees. And to find this angle, we will use opposite over adjacent, and VL minus VC over VR. That will give us that value. So in an inductive circuit, supply voltage leads the current by that much, those many degrees. Now, if we want to draw the resistance and reactance values, then XL is drawn here, XC is drawn there, because voltages have got exactly opposite phase. So these reactance and resistance values have to be drawn like vectors. And again, it's the same method. XL minus XC will give the total reactance. And then if we add R, that will give us the total impedance. And by adding them in a vector manner, that's how we will do it, as you can see from these formula. Now let's move on to what happens if the XC is more than XL. If XC is more than XL, then obviously VC will be more than VL. And if VC is more than VL, then it becomes like a capacitative circuit. So even though there is inductor is there, but the circuit behaves like as if the inductor wasn't there and it was only a capacitor and a resistor. So again, we add them phases like vectors. So because they've got opposite phase, so VC minus VL will give us this much size. So this is like becoming like a capacitative circuit. Add VR in a vector manner, that will give us the supply voltage, and supply voltage square will be equal to this square plus that square, that is this square plus that square. And since current is always along VR, is in phase with the voltage across the resistor, so we say now all these phases move in an anti-clockwise direction. So we can see from here the supply voltage lags the current by those many degrees, or that supply voltage lags current by those many degrees. And we can use tan theta to find out this value. How do we find the total impedance in a capacitative circuit? Again, because voltages are added in a vector manner, the reactances will be added in a vector manner, XL and XC over here, and then XC minus XL will be the difference of these two, and then R is along here, and that gave us the total impedance. And the formula will be Z square, this one square will be equal to this square plus that square, and tan of this angle will be opposite over adjacent, XC minus XL over R. So that's for a capacitive circuit. So just summarizing, in a capacitive circuit, VC or XC is more than VL or XL. And so that will be called a capacitive circuit. And an inductive circuit, XL will be more than XC, and therefore there will be VL will be greater than VC. So that's all for today's lesson. Thank you for watching it.